Real pleasure to be able to introduce Professor Jinwoo Hwang from Ohio State University, who is an expert in scanning tunneling electron microscopy. And he got his bachelor's degree in material science and engineering in 2002 from Hwang University in Korea. Afterwards, he did his master's degree at the University of Philadelphia before going on and doing his PhD degree, also in material science and engineering at the University of Wisconsin in Madison. Then he spent some time at the University of California, Santa Barbara as a postdoc before joining the faculty at Ohio State University. And today he will be telling us something more about his research, in particular on using microscopy for point defects in gallium oxide, the material everyone should know is one of the most interesting materials, in particular because I'm also working on it. So with that, please go ahead, Jinwoo.
Thank you very much for the very nice introduction. It's my great pleasure to speak today in your seminar series as the first speaker of the semester. Again, I'm Jinwoo Hwang from Ohio State University. Today I will speak on the atomic scale microscopy of point defects and their complexes in ultra-wide bandgap gallium oxide. Okay, so this is something that I've been working on for about 3 years now as a part of the MURI project that we got support from the Air Force Office of Research. All right, so with that, I'd like to begin with a very broad background about the wide bandgap materials. Now, as you already know, now the bandgap, when you think about the bandgap of semiconductors, now you think of silicon first, and silicon has the bandgap of 1.1 EV, and that's what gives you this semiconducting property. You have to have this bandgap. So okay, so that's the most common material, right? So okay, but if you think about the other materials that has either narrower bandgap or wider bandgap, then we have more choices. And we are especially more interested in this wide bandgap material that's having the bandgap between around 1.2 to around 4 to even 6. So there are a lot of different kinds, especially with the newer oxide and other things. There have been a lot of materials that has been under investigation. One thing that was very successful, of course, is gallium nitride that has bandgap of 3.5 or something, and especially this one is has been very successful for displays and everything, and people get Nobel Prize and everything, right? So now, if you go even further, like above, let's say 4 electron volt, then we have a very large bandgap materials. Now, at this point, we could say, all right, it's because the bandgap is so wide that we could say this is ultra-wide bandgap material. So it's just the extra ultra that we're putting here. So diamond has been around for a while, maybe 30 years or so. My own uncle got his PhD with diamond, never took off. He's doing well, by the way. But now the newer material is kind of getting attention, and that is gallium oxide. Of course, the material itself has been around for a long time, but now people are putting their effort to understand this material better and then develop this into wide bandgap applications. So why do we care about wide bandgap applications? I just put some pictures of very few examples. Now, as I said, this is funded by Air Force, and obviously because they're interested in this in defense applications, radars, high energy weapons, electrical systems, and catapults. The systems that uses extreme conditions. So this is part of the effort to develop the materials at extreme conditions. For more civilian or daily life application, there can be power grids, very large market. And also the electric vehicles or small electronic gadgets such as the adapter, right? So if you have the wide bandgap used for the adapter, then the form factor becomes smaller with higher throughput, right? So there's a lot of the efficiency increase that we can gain by using this type of material, and that if you scale up, one example could be the high-speed train like this, which Japan has tested recently, and then demonstrated 35% reduction in power conversion loss and 20% weight reduction in traction system when they replace the silicon-based diode with the silicon carbide wide bandgap Schottky barrier diode. Okay. All right. So there's tons of the good applications that can be realized when we have this type of new wide bandgap material. Now, in more specifically, the gallium oxide. If I give you more details. Now, this thing, as you can see, is an oxide, so it does have oxide, and then it's transparent too, which is really good, right? So if you have a piece of gallium oxide, it's pretty transparent, as you can see. So it actually gives quite viable, like the potential for being used for the optical and photonic applications as well. So among maybe 3 or 4 different phases, beta phase is the most stable one. And then as I said earlier, the band gap of this beta phase is about 4.8 eV. And again, it's transparent. And most importantly, gallium oxide has this high breakdown voltage, which is very important. And therefore, it becomes a very good candidate for high performance power device application material. Okay. Yeah. And one very important technical aspect or advantage is that this gallium oxide is not only for the thin film, such as, if you look at the gallium nitride, usually they are the thin films, right? And then the substrate has to be something else, because if you try to make the bulk gallium nitride, that bulk growth is very difficult and also very expensive, which is not the case in gallium oxide. Gallium oxide can be easily grown into bulk crystals, and that's pretty cheap. Not as cheap as sapphire, for example, but it's still pretty cheap. So if you have the gallium oxide substrate to begin with, it already gives you tremendous flexibility in terms of how you design the whole structure, homoepitaxy, heteroepitaxy, or anything, right? Yeah. So recently, the thin film growth using molecular beam epitaxy or CBD has been very extensively studied, and our collaborators at OSU and other universities have been working on such growth methodology. So this particular plot here is comparing gallium oxide with other materials, other wide bandgap materials such as silicon carbide or gallium nitride. You can see some of the properties are way better. As I said, critical electric field, which is related to the high breakdown voltage, it's way higher than other materials. And then the band gap is also high. But there are other drawbacks too. The electron mobility is actually smaller than others. And also thermal conductivity is also small. But these drawbacks are something that we can handle. And so, some of the examples of how we handle those include, making alloy with gallium oxide, and in between the gallium oxide and aluminum oxide, for example. Then there's a way to handle the electron mobility issue. And then thermal conductivity may become just a design issue, how we design exactly the device and the interface. Okay. So it's a pretty good candidate for the wide bandgap application. So device per people that we work with, they try to make this gallium oxide device work. But at the level of material science, there are a lot of unexplained the problems that still exist within the atomic scale structure. How we understand the structure and then connect that to the existing problems. That's something that hasn't been done so far. Okay. So for example, there are properties such as the properties that are important to understand, such as the formation of defect traps, which I'll explain very soon. And then the doping efficiency. You want to dope this much, this much, you want to achieve this much doping concentration, but it's lower than that, right? And then you want to have N-type and P-type, but N-type is easy. In fact, it's automatic, but the P-type doping is pretty difficult, right? And then, so that means some kind of compensation. You dope the material, and then many of the dopants become compensated. So those are issues that exist. And all of these problems or the issues that we don't understand revolve around the nature of the point defects within the atomic scale structure. So when you say point defect, then it's a defect at the level of atomic scale, right? So if you look at the structure of gallium oxide, you of course have gallium atom and the oxygen atoms, the red ones. So sometimes you miss all these, the cation or oxygen atoms that becomes vacancies, or that they can be replaced with substitutional, dopants like tin atoms, which I'll show you pretty soon. So those are all different types of defects, right? And then also you can have interstitial defects, like the tin atom being stuck in the interstitial position, or silicon or something else can all go to the interstitial sites. And then all these defects can cluster or either pair or cluster to form defect complexes, which I'll show you in a moment. Okay, and then those defects can be also related to extended defects of various kinds. So understanding the atomic scale defects and correlate those to the known problems or properties is very important. And that's what we are trying to do using the electron microscopy. All right, so what has been done in the past before I get involved, like 3 years ago, what has been already done is first the density functional theory calculation of the properties and the structure. And the work here is done by Chris van der Waal at UCSB, which I'll explain in more detail later. So now this is the prediction or calculation by theory. And then one popular way of measuring the defect trap state is using deep level optical spectroscopy, and that's done by our collaborator Steve Ringel at OSU. So what they do is they measure the defect trap state in between the band gap. So now if you look at the band gap, obviously if you have nothing, no doping or anything, you expect nothing showing up in between. There shouldn't be anything between conduction and valence band, but you get a lot of stuff here, right? The length of the bar represents the concentration, and then that's the corresponding energy, meaning that something is there in the structure and then causing these trap states. And it's our job, it's our goal to identify what those are, right? So in order to identify, you actually have to look at the structure and tell what's there. And that's how we get involved here. So what we are trying to do is using the atomic scale microscopy to look at the atomic structure to connect these two, right? The theory, actually three, the theory and properties and the actual structure. So we understand how these are all correlated to each other, right? So that's how we contribute here. Okay, so we want to get we want to achieve the direct observation of the physical picture of the atomic scale structure and defect that directly relate to the electronic and optical properties, right? Okay, so a little bit of background of our technique. So it's a scanning transmission electron microscopy. So transmission here means that our electron beam is penetrating through the sample, and then we get the signal, and then we analyze the signal to get the atomic scale information. All right, so some of you may be familiar with just transmission electron microscopy, and now this is not the same. This is scanning transmission electron microscopy. So when you have just TEM, that usually means that you're using the electron plane wave. So in that case, if you just have TEM, that is very similar to what you are used to, the optical microscopy. It's just that you replace the visible light with electron wave, then that becomes essentially transmission electron microscopy. But scanning transmission electron microscopy is a little different. So in this case, what we are doing is we converge the electron beam on in a way that it's going to form a very small probe with the tip size of about 1 angstrom, which is comparable to the size of atom, or even smaller, right? So that gives us the atomic spatial resolution. So when we probe the electron probe, I mean, when we place the electron probe onto a sample, essentially we are probing 1 atom at a time, or 1 atomic column at a time. And what happens is that the incoming electron is going to interact with those atoms, more specifically the electrons that orbits the nucleus. And that interaction is going to provide the scattering events, right? And then those scattered electrons is going to scatter in many different ways. And then we place these detectors in many different positions, and then get the scattered information. So depending on where you get the scattered information, that provides different information. For example, if you have a CCD type detector that is placed directly underneath the electron beam, then this is going to give you diffraction pattern, which is very similar to X-ray diffraction pattern or neutron diffraction pattern. Okay. Or you can have a spectrometer underneath it to analyze the energy loss of the incoming electron by the interaction or the scattering itself, to have some chemical sensitivity so that you can tell, oh, okay, this atom is gold, that atom is silver or iron or etc. The signal among these many kinds of signals, the one signal that we're relying on is what we call annular dark field signal, or which is collected by this donut type detector. So if you see this schematic diagram, the donut is covering the high angle scattering area, meaning that, okay, so these are the electrons that are scattered with relatively higher angles. And this information is in fact very important, because that scattering information is mostly related to the Z number of the constituent atoms, or also their numbers too. Okay, so those are that's the primary method that we use to determine the structure, and also also getting some chemistry information. So this is the one example that I'm showing here, which is potassium tantalate grown on gadolinium scandate. We are looking at the interface. Now that's the growth film growth direction. So as you can see, we can resolve all the atoms, even smaller ones such as potassium. And then something's happening at the interface. And then what we figured out in this case was that, okay, so the structure gets reconstructed, okay, right at the interface. Now, such information is something that you cannot get with X-ray, because X-ray beam is so large that the whole information is average. So you don't get any localized information. But using this annular detector and the scanning electron beam, we can get all the details of what's happening at the atomic scale. All right, so using this, now if we apply this technique to look at the gallium oxide structure, then you get something like this. This is the same mode that I just explained, and using the annular dark field mode, you get an image like this. And in this case, because the gallium atoms are heavier than oxygen atom, mostly you see this the intensity from the gallium positions, right? So all these positions are gallium positions, and then the length scale is 2 nanometer here. Okay. All right, so then, but you can also use some other modes to be able to detect the oxygen positions. One example is something we call the integrated differential phase contrast mode, and you can see the oxygen atom positions are also showing up. So that's great, because now we can compare what we know about the structure and what we see here. If you compare these two to each other, but then there's a perfect match. That's great. Okay, so we can get all these the atomic scale details, and this confirms that. But okay, so what's the point? Because the structure was already known from other measurement, and we just confirmed it, and that's not the point of our work, right? So our purpose of using this type of technique, the scanning transmission electron microscopy, is using the high spatial resolution to examine the point defects, like a very small defects such as point defects and complexes. Okay, that's what I'm going to show you later on. Okay, so back to the figure that I showed you, right? So what we want to do is to establish the correlation between what has been predicted and what has been measured property-wise, and then the structure that we directly observe, right? Okay, so the first problem that we are trying to tackle is, how do we understand these defect formation, and then how do we correlate those defect trap states in to any of the observed structure, and how that compares to the theory, right? So that's the three-way comparison that we are trying to establish here. So we looked at, the first sample we looked at was the bulk gallium oxide. This is like the substrate, right? So we didn't start with the film first, because we had the bulk substrate. We started with that first, and then the bulk substrate was doped with tin atoms, and then this is the doping concentration, nearly about 10 to the 19th, which is pretty high. Okay, and then we are looking at an area where nothing, not much is happening. So this is a regular area. Okay, so then now again, these are all gallium atom positions, but then we have to define those positions first to make it easier for everyone to understand, because this is a very anisotropic structure. So it is not like a regular face-centered cubic, right? So this is a monoclinic structure that is very anisotropic. So there are two different gallium positions. One is green one here, which is tetrahedrally coordinated, meaning that there are 4 oxygens nearby. And then there are other type, which is there's another type, which is gallium 2 site, what we call gallium 2 site, the blue one, and that is octahedrally coordinated, which means that there are 6 oxygens nearby. Okay, so there are two gallium positions. And then there are 3 different oxygen positions, which are colored differently, but less important for the matter that we discuss here. All right, so those are the atom positions. But then I want to point out the fact that there are also a lot of empty gaps in between those atomic columns, and those become potentially the interstitial sites, right? So it's possible that the defect can form right at that position, meaning that some atoms, whatever that is, can be stuck at the gap here, right? Okay, so what are those gaps then? Let's define those interstitial sites. So we name them interstitial A, interstitial B, interstitial C sites. It's following the original notation that Chris van der Waal at UCSB has used, so we just follow that. So this one right here, dark blue, is the interstitial A site. This is the B site, and this is C site. And later there will be 2 more, which we call interstitial D and interstitial E sites. Those are the experimental ones. Those are the ones that we observed for the first time, and I'm going to show you what those are later. Okay, so now we define all these positions, and then we look at the sample, the same sample but different area of the sample. Then what we look at, what we find was something like this. Now this is from the same sample but different area. But as you can notice, there are a lot of extra intensities that are showing up in many different positions, as you can notice, right? As compared to what you see here, you get a lot of extra signals. Okay, so let's point out where they are exactly. And this is the exact location of those extra intensity. And then those are the type, right? Okay, so we identify that this is IB type, which means it's this location right here. And the red ones are the IC type, which means that it's the gap right here. Okay. All right. So yeah, it looks like they're pretty clustered, right, in this particular area. All right. So that's that was the first observation. We were very excited because it's actually, even with this atomic scale resolution, it is very rare to be able to observe these individual interstitial atoms or columns, right? Because they are very hard to see. So it's not just the spatial resolution that we have, but also it's the fact that the very anisotropic structure, the monoclinic structure, is actually helping us to see them, because in some orientation, the gap appears to be so large that it becomes much easier for us to observe these interstitial atoms as compared to other materials like gallium nitride or silicon. Okay, all right. So are we looking at the extra intensity? Are they real? Because some may say they're noise, right? They're not noise. If you see that position right there, you're supposed to not have anything, so it's supposed to be flat, but there's a peak, right? Okay, so this is not noise. This is a peak, right? Okay, so more detail right here. This is again, this is interstitial B site right here, and that is the IC site, the red one right here, right? Okay, so those are, yeah, and then they are, as I mentioned earlier, they are kind of clustered, right? So if you look at the nanoscale overview, a more kind of zoomed out version of the figure, then you can see there are higher concentration in this area and in that area as compared to some other areas like this. So they tend to cluster a little bit. Okay, so the density functional theory has calculated that the formation energy is the lowest with the IC site, and then the highest is IA site. Now that actually is consistent to the number density that we calculate. Although this is a very small sampling, it turns out that the most number is seen with the IC site, And then IB side is the next, which is the light blue one. And then we didn't see much of the IA side, meaning that they are hard to form according to the formation energy that's consistent. Okay. All right, that happened. Okay, so that was pretty exciting, right? Because now we were able to see the interstitial atoms, or it was interstitial, like a clustering, individual column of those interstitial clustering, which is very rare thing that we can expect to see. But we saw that in this material. But then what is that? What does that tell you, right? So that's the thing. What is the important information that we can extract from it, right? Okay, so now for that matter, we have to go back to this theory that I briefly showed you. So now again, this is the paper that's published by our collaborators back in 2012, before we worked with them. So now this particular paper was actually very important. It turns out this paper was very insightful. So what this was telling was, okay, so the paper is describing the formation of point defects and complexes. And what the paper was predicting was, if there is a vacant gallium-1 site, right, the tetrahedral site, right? Okay, so if there is a vacancy, which can form naturally in any, like in any material, but in this material, if the vacancy is formed at the tetrahedral gallium-1 site, then that configuration is in fact not energetically stable. So it has a high energy state. So whenever you have this vacancy, what happens is then, okay, so system doesn't want this anymore. Therefore, what happens is, what likely is gonna happen is the neighboring gallium-1 site atom, another tetrahedral atom, can jump into the interstitial site. Okay, so then what happens? Okay, so that atom jumped into the interstitial site, meaning, okay, so there now you have an interstitial atom defect itself. So now that's what we're seeing, right? So those are all interstitial atoms. So now we have this jumped, the atom jumping into this site, which creates another vacancy. Okay, so you end up having two vacancies and one interstitial atom, and they are all paired, right? So they make their own complex. It's a new type of complex that that appears, that was predicted by the theory, right? So we can say this complex as interstitial-divacancy complex, because it has one interstitial and two vacancies, right? Okay, so that's what the theory has predicted before. So what that means is, if we are looking at these interstitial atoms, meaning that we are looking at these atoms, right? They appear to be a lot of them, right? Okay, so then if they are there, then if this theory is correct, then we also need to be able to see the vacancies too, right? So that's the thing. So that's why we wanted to do further quantification and try to see. Let me see if I can minimize. Yeah, okay. That way I can reach my figures here. Okay, so now, so what we try here is, rather than just looking at the intensity of the image, we quantify the intensity so that we can tell whether we can verify the location of these individual vacancies, in addition to the extra intensity that comes from the interstitial atom. Okay, so if you look at the experiment here, you have an area where there's no defect, right? So this one does not show any the extra intensity. So line profile of that would give you just two peaks: one gallium column, nothing, and or the other gallium column. Now, if you draw the same intensity profile across the area where there is intensity, the extra intensity from the interstitial position, of course, because of this extra column here, the interstitial column, you're going to have this extra intensity. But interestingly, the nearby gallium column intensity is always going to be low. So what that means is, as I said earlier, the image intensity depends on the number of atoms, right? Because this is a high angle scattering. So the fact that the gallium column intensity is lower means that this column is actually missing atoms. So missing atom means vacancy, right? So that way we can confirm that, okay, this column actually contains vacancies. So whenever we have this extra intensity from the interstitial column, then we have vacancies. So they are almost always paired. And that way we were able to confirm that whenever we see the interstitial, it's actually showing us the the interstitial-divacancy complex. Okay, so we also ran simulation, the image simulation from the model. So we constructed the model that we think is happening. So this is the area where there's no defect, and this is the area where we introduce the defect, and the same thing is happening, right? So intensity, when you have the interstitial column, you have the intensity, but when vacancies, same number of vacancies introduced, then you get the lowered intensity. Okay, so computationally, there was also it was possible to recreate what we saw in the experiment. Okay, yeah, so that's how we confirmed the interstitial-divacancy complex. But this one was revolving around, I mean, nearby the IC side, the red X here. But then we also see the same thing surrounding the IB side as well. So the same exact thing happens. It's the same mechanism and same intensity going up and down, but it is happening surrounding the IB side. Okay, so the complex formation happens both surrounding the IC and IB side. We were able to see both of them. All right, so that was a pretty exciting discovery, because we were able to confirm the structure, the very unusual structure that was predicted earlier, and that was done by this direct observation. And then one other thing that we did here, although I cannot go into all the details here, one other thing that we did was, okay, so if we are seeing the interstitial atom and the vacancies, are we able to actually count the number of those atoms? Okay, so that's so we went deeper in the analysis and then try to get that number, right? So we actually did, and these graphs are in fact showing the numbers. But then, as I mentioned earlier, the signal here is not only dependent on the number of atoms within this column, but also the Z number, the mass of the atom, also affects the intensity. Meaning that if the cation in the interstitial that is placed here is tin, then it's going to be, the intensity is going to be higher. So the depending on whether the tin atom, I mean the cation is either tin or gallium, that's going to change our intensity. So we cannot get to the unique solution for the number of atoms that are placed right here. Okay, so that's the question, whether the cation is gallium or tin, because it can be either way, right? So because this is heavily tin doped, it's certainly possible that these cations are tin. Okay, so speaking of tin, then, so the theory has provided the likelihood of this tin atom being the most stable at this position right here, which is the octahedral position, and that was also observed in some of our experimental samples. As you can see here. So right here, you have higher intensity. This is the profile. As you can see, the profile has higher intensity. And that is because the tin atom here is heavier than gallium. And therefore, the intensity comes out to be higher. So in some cases, we can actually detect them, right? Okay, so it's kind of, I mean, we have only one, proof of that. But we do have confirmation that tin can go to the octahedral side. But the more difficult question to answer is what does the tin doping do to the concentration of these complexes, defect complexes that we observed, right? So is it do we have those the large number of complexes because the tin goes into the cation side, or is it something else, right? So that's something that we were discussing with our theory collaborators. So the hypothesis that we came up with is that when we have tin in high concentration, they may promote the formation of vacancy interstitial complex in certain way. And that way is like this, okay? So tin can drive the material more n-type because it's an n-type dopant. So that can also stimulate the formation of the compensating acceptors, such as the gallium vacancy or the complex itself. So presuming a reduction in vacancy formation energy for increased Fermi level energy, tin doping may facilitate this increase in vacancy concentration through increase in Fermi level energy. Okay, so in other words, okay, the tin doping, if we increase the doping concentration, the tin doesn't have to go into the interstitial site by themselves. But even if they don't do it, it can perhaps increase the chance of gallium atoms, just regular, the host gallium atoms, to jump into those interstitial sites. Okay. All right. To confirm that the hypothesis, what we need to do is that, okay, so we have to look at another sample that has lower doping concentration. As I said, one sample that I already showed you is the one that is heavily tin doped. So the doping concentration, or carrier concentration, I should say, was near 10 to the 19th. So what if we look at the sample that is not doped? Okay, so this was doped, but this is not doped. Okay, but this sample, the gallium oxide, substrates, they tend to be already doped naturally, right? So even if you don't intentionally dope the sample, it does have carrier concentration of about 10 to the 17th. So that's why we call this unintentionally doped. But one thing for sure is this one does not have tin, because you get tin only if you intentionally put them, right? So at least we know that there's no tin here. So what we observed in this other sample was that this actually also showed those formation of complexes, but much lower in numbers. So what that means is that, okay, complex can form even without the presence of tin atoms. So what that means is that whenever we see the interstitial atom, they should be gallium atoms rather than tin, because there's no tin in this case. But their number density greatly increase as we increase the tin doping concentration, as we saw in this figure. So what that means is tin doping really facilitates the formation of this dopant. The defect concentration, even if the cation interstitial is gallium, not tin. Okay. All right. So that's the conclusion that we can draw from this particular comparison. So this was our STEM experiment showing the increase in the number of complexes as a function of tin doping concentration. Now, if you compare that to what our collaborator has measured using deep level optical spectroscopy, again, this is the way to measure the trap level concentration of trap states. And what they saw was when the tin doping concentration was increased, this particular one has changed this concentration. So, and in fact, this was the only one that showed the change in concentration. So same trend was shown then, right? So the tin doping concentration increased the number density of the complexes here, and also this one had the same behavior. So we can make the correlation. So it's very likely that this particular trap state is correlated to the formation of the defect complexes that we observed here. So that's how we made the correlation. Okay. So this particular one has the energy of EC minus about 2 eV. So that's about 2 electron volts apart from the conduction band here. And then one other thing that we can correlate is what DFT says about the energy, the defect energy. So when the interstitial-divacancy complex forms, the theory suggests that the value of the trap state energy would be somewhere around here. The calculation does not actually give the exact number, but the ballpark figure is somewhere around there, which includes the number that's also measured. So, okay, so that's also something we can correlate. So there's a three-way correlation between what's predicted by the theory, what is measured by the optical spectroscopy, and the direct observation by microscopy. Okay, so that's what we were able to do here. All right. Okay, so that's about the formation of complexes. Now, some extra information that I can also show you is the formation of this other type, which we named as interstitial D site intensity, as well as the interstitial E site. So now these weren't considered before in any of the DFT or atomic scale model, but there were some extra intensity showing up, so that we saw them. And then, interestingly, whenever this ID site intensity is there, they were always paired with 2 IC site intensities. It was always the case. And when they, same way, when there was IE site intensity, they were always paired by 2 neighboring IB site intensities. So this is kind of like looking at bigger scale complex formation. And as you can see, they are always paired. So there's no occasion where ID appears without two ICs, and the same here, right? So IE always appear with pairing IB the intensities, right? We thought this was very interesting, but there was no model or defect formation, like a mechanism that can explain this. But we were able to go deep in the quantitative analysis of all the intensities. I cannot go into all the details, but I can show you the finding, right? So all these models were constructed just based on the experiment. There's no energy minimization or any kind. There's no MDDFT. This is purely experimentally driven schematic of the model. So what we found is happening is secondary relaxation, essentially, when there is two neighboring interstitial-divacancy complex. So this complex right here is something that I already explained, right? So the extra jumping here, so that creates another vacancy. So you have one complex here. What if there's another complex forms right next to it? Okay, so if that happens, then you actually have an empty space in between, which is pretty large. Intuitively, you think this is a little unnatural. In fact, what happens is we figured this atom jumps into that site, which we named as ID site. Okay, so that atom jumps into the ID site, so it actually bridges, this structure and that structure. Okay, so that's what's formed here. So now, so that's this one right here. So what you're looking at here is the ID site intensity from right here, which is this one, and two IC site intensity, which is this and this. Okay, so they're always paired. So this is kind of a secondary relaxation that we saw here, and we wanted to see, well, okay, so that's experimentally seen. So we wanted to calculate the energy of the whole formation, but that was actually very difficult to do. Perhaps I should ask Hartwin to try it, but our collaborators at so far they were not able to deal with the large structure in their DFT simulation. So it was pretty difficult. But okay, well, okay, that was at least we have the experimental confirmation of the structure, and this one is involving IC and ID, and same exact thing happens involving IB and IE. So when you have one complex and the other right next to each other, then you have the gap, and that gap is eventually bridged by the jumping of this atom. So now you have this atom jumped from the original position, creating another vacancy, and then that ends up being here, so creating another interstitial intensity, which is the IE side. Okay, so same exact thing happens involving the IE side as well. So although the DFT wasn't able to model the whole thing and calculate the energy, our collaborator Joel Varley at Lawrence Livermore lab pointed out the fact that this structure, the relaxed structure, in fact has a high similarity to the other gallium oxide phase, which is gamma gallium oxide phase. Now, if you look at the gamma structure, you have this one row of atom you can recognize, right? And then the other row of atoms, which actually is very similar to what we have here, one row of atom and the other row of atom. So now it's the same thing, right? So one row and the other. And then these two rows are bridged by the few atoms in between. And that's similar to what happens here, okay? Although they are not exactly the same. So now we're not trying to say that this is a phase transformation. One, because the structure doesn't match completely. And also, even if this is some kind of phase transformation driven event, it's very localized. And then the lattice is not defined, so it's definitely not a complete phase transformation. But at least we have the signature of such evolution of the phase toward the direction to the structure that resembles the metastable gamma phase. Okay, so that's what we found here. And gamma phase is something that I'm going to explain in a few moments when I get to the aluminum gallium oxide too. Okay, so I think, yeah, so that's the end of gallium oxide part that I wanted to show you today. And for the last 10 minutes or so, I can go into a little bit of the aluminum gallium oxide story, okay? So this material, as you can see, is based on beta gallium oxide, but now aluminum atoms are involved, right? So basically it's an alloying between gallium oxide and aluminum oxide or sapphire, right? So why we are doing this? Okay, so this is, in fact, if you know the background a little bit, I don't know much, but what I know is that gallium nitride, so that's very popular, right? But then the community has been trying to get aluminum involved. So you have aluminum nitride and gallium nitride mixed together so that you can achieve things, right? So, you know, the purpose is the same here, right? So you get the alloying of aluminum oxide and gallium oxide. And why are you doing that, right? Because you want to form, for example, two-dimensional electron gas at the interface that can increase the channel mobility, which is actually low if you just have the gallium oxide interface. So that's one thing you can achieve. And the other thing is that the aluminum oxide, it's almost insulator, right? So it has a very large band gap. So in fact, by introducing aluminum, you can actually tune the band gap. Band gap can actually be larger. There's a potential to also tune the breakdown voltage and everything. So, and apparently making aluminum gallium oxide is easier than aluminum gallium nitride, meaning it's very promising, right? So the material, the defect level is very low when you do this type of alloying. So it's a very promising method that has been studied extensively for the last couple of years or so. Okay, so that's what our device people are doing, our collaborators are doing. But then the question is then, okay, so there's a problem, right? Because when you are trying to grow these aluminum gallium oxide, you don't always get the structure that you want, right? So in fact, Hwang has explored the structure before a couple of years ago, and this is a very important paper predicting the stable phase when the alloying is happening, right? So what you're looking at is sapphire, which has corundum structure, and the other is gallium oxide that has monoclinic. Then which one is going to win? That's the question, right? So he calculated that. And then if you calculate that as a function of the aluminum concentration, then monoclinic, in fact, is going to be stable up to the aluminum concentration of about 70%. That's pretty high. So that's pretty intriguing, right? Because, and also promising because, okay, so we want to keep the beta structure, and that's the monoclinic structure, right? And it turns out when the growth happens, that's the case, right? So most of the cases, the beta phase is being obtained. I mean, they preserve the original structure. Okay, so this prediction is correct. But then what happened? What people have noticed is that locally, in a very local region like this, there's something else happening, like this one, for example, right? So this is not either monoclinic or corundum, but it's something else that people didn't recognize initially. But later we figured that this is actually a formation of gamma phase that I showed you a few slides ago. So in fact, the gamma phase formation is very common. For some reason, gamma phase is likely to form, especially at the aluminum gallium oxide. Maybe it has something to do with the strain because of the lattice mismatch. But the gamma phase formation is pretty commonly observed in this type of growth. Okay, so if you look at the entire film of aluminum gallium oxide, now we have looked at in different aluminum concentration. This has 16% aluminum, so it's increasing, 22% aluminum, 27%, 40%. Now, as you can see, at lower aluminum concentration, the overall structure is pretty good, as you can see. But as you increase the aluminum concentration, the structure becomes a little degrading, right? So if you go to 40% aluminum, you can see the growth growth of beta phase only extends to about 5 to 10 nanometer, and then after that, the structure becomes defective. Okay, so what that means is this is realistic critical thickness, and this essentially have become the critical concentration, only 40%, which is way lower than what has predicted here. So what's the reason for it? And then that puzzled everybody. And then we were trying to find the answer for it. So the answer might be related to the fact that the calculation here is, if I'm correct, Hwang, I think the calculation here was assuming equilibrium state, mostly about bulk, and therefore at that equilibrium assumption, all the aluminum atoms should be occupying octahedral sites. I think that's assumed here. But so that's bulk, the case of bulk, but this is thin film, so there's a difference, right? So therefore, maybe what's happening is, okay, in this thin film growth where things are non-equilibrium, the aluminum atoms may occupy the other sites too, which is tetrahedral sites. So we wanted to understand that aluminum incorporation, whether they actually go into tetrahedral sites or not, okay? So that's what we wanted to do. And we did that, okay? So again, there are a lot of details here which I can't explain all, in limited amount of time. But what we basically did was the same quantitative STEM intensity analysis for all these samples having different aluminum concentration: 16, 22, 27, and 40%, up to 40%. So throughout the entire aluminum concentration that we explored here, the answer, the final result of the analysis here is actually plotted here, which shows the aluminum occupancy at both sides. One is gallium, one side tetrahedral site, and the other is octahedral site for entire concentration, composition, aluminum composition that we looked at. So what we found was, regardless of the aluminum composition, in fact, gallium-2 site is 54% occupied, and tetrahedral site is 46% occupied by aluminum. So what that means is, unlike the equilibrium case where gallium-2 site needs to be 100 and the other being 0, this non-equilibrium film growths don't end up like that, right? So they end up having the octahedral aluminiums about 54% of the time, and then the other side is going to be occupied 46% of the time. So it's almost half and half. So therefore, it doesn't always occupy this side only, and therefore that's where we see this deviation between what's the number here, which is 70%, and the 40% here. And that's it's likely that that is what's limiting the growth of the structure at high aluminum composition. So okay, so with that, so our collaborator Chris van der Wal and their postdocs have come up with new simulation of what might be happening in the growth. Now, okay, so they assume that, okay, so this is unlike the bulk growth or the bulk state that they simulated before. Now maybe their hypothesis was that, okay, so maybe during the growth procedure, the surface diffusion kinetics may dominate, and then that may end up giving lots of aluminiums end up in tetrahedral sites. And then that's what they simulated here. I actually don't know all the details, so I won't explain all the details. But the simulation results confirms that because the process is controlled by the kinetics of the surface diffusion, it is likely that the sum of the aluminum atoms can end up being at the tetrahedral site, well, even though the energy level is higher at that site as compared to the octahedral site. All right, then finally, one other thing that was very noticeable was the formation of this planar defect in aluminum gallium oxide. In fact, this was very commonly observed, right? As you can see, there's a line of defect, which means it's a planar defect. So we were very puzzled by this formation because, first of all, we don't want to have this type of extended defect in your structure because it's going to limit your mobility and all that. But then the formation mechanism itself is also in question, right? So what we found out by doing the quantitative STEM analysis was that this formation is in fact directly related to the local aluminum concentration. Now what we did was we exactly figured out the structure within the line of defect, which is explained here. And another thing is by looking at the column intensity, we figured out the local aluminum concentration, and that plot is shown here. So now the x-axis here is the distance from the defect, right? So, okay, so this is a defect, and that's the distance from the defect, either going up or down, right? It's all combined. And then this is the aluminum concentration. So as you go closer to the defect, this direction or that direction, right? So as you go closer to the defect, as you can see, the aluminum concentration is increasing. And then you go further, then it goes back to the nominal concentration. Okay. So what that tells us is that during the growth process, for some reason, there was gallium deficiency, right? If that happens, then the structure becomes defective, right? And then, in fact, that defective structure is very similar to gamma phase that I showed you earlier. So this again relates to the secondary relaxation that I showed you earlier, right? So when the aluminum is concentration is locally high during the growth, it actually relaxes in a way that it resembles the gamma phase, although this is not a complete phase transformation. The structure becomes more like the gamma phase. But then after that, if the condition improves and gallium deficiency is resolved, then the structure is recovers to the monocline structure. Okay, but that's in case of lower aluminum concentration. If this is very important, because if aluminum concentration is high, then this can be the end of the growth. This can be, so what's grown below this defect can be the critical thickness. So in fact, the formation of defect therefore can limit the critical thickness of the film. Okay. So, and then what we provide here is the evidence, the experimental evidence that the local aluminum concentration or fluctuation of aluminum concentration over time during the growth is closely related to the formation of this planar defect as well as the critical thickness of the beta phase film. Okay, yeah, so that's the answer that we were able to provide here to help developing the growth mechanism. Okay, all right, so that's in fact the end of my slides. I would like to thank my postdoc who actually left 2 weeks ago, get a job in the industry. And then now it's taken care of by 2 students, Steve and the other one, which I forgot to show here. And this is our team member. I mostly work with Siddharth Rajan, who is an MBE grower, and Hongping Zhao at OSU, who does MOCVD growth, and then Chris Van der Waal at UCSB, who takes care of the DFT simulation. And finally, I would like to acknowledge our funding source, Air Force Office of Scientific Research. Thank you very much, and I will take any questions.
Okay, thank you very much for the very nice talk. So while it's already 5 o'clock, we still have some time for questions, but if you have to leave, feel free to leave the Zoom call. So are there any questions? Yes, Mohammed.
Hello. Yeah, I like the talk, but I'm not very good in this condensed matter physics stuff. But yeah, I have a small question.
Sure.
The band gap energy that you showed, it's almost like 4.84 eV. So
yeah.
Yeah.
So if I go to all the way top there.
Yeah, here.
Yeah. Okay. You mean here?
Yeah. Right.
Yeah. Okay.
Yeah. Yeah. So so I see that the like x-axis, which is like k-axis, it's not uniform, right? Like the two. But how do you measure the like band gap energy with this non-uniform EC and E structure? Like, do you take the band gap energy to be at k is equal to 0, or do you take the average of those things?
You mean you're looking at this one, right?
Right.
Yeah. So that's the DOS measurement, and so I'm actually not a good person to provide all the details, unfortunately. Yeah. So that's that's actually out of my area. Yeah. So unfortunately, it's a little difficult to say anything more than what I already provided. Yeah.
Okay, no problem.
Yeah, sorry about that. Yeah.
No, it's okay.
Yeah.
Judy?
I think Judy has a problem. Question.
Yeah.
Judy, I think you're muted. Are you? Oh, no,
okay.
You're not.
Sure.
Yeah. Hi. Yeah.
Okay. Hi. Sorry, I missed the earlier part I was teaching.
That's okay.
For the mixture, say, doped, like a gallium oxide with aluminum,
Yeah.
thin film case, you talk
Right.
about also the importance of the thickness, right, for the formation
Right.
of
Yeah.
So why thickness matter? Is that because of the lattice mismatch between substrate and film? So up to certain thickness, then the strand will be kind of changed in terms of the intensity or something else.
Yeah, so yeah, that's an important point. Although I didn't really elaborate it, but there is a there can be some effect of strain as well, because if you increase the aluminum concentration, it's not just that the phase itself is whether either it's stable or not, but also it's about how much strain is building up from the substrate, right? So I think the both matters for the stability of the phase, and then it eventually determines the how far it can go when it's being grown.
Right.
Yeah.
Okay.
Yeah.
So that's why I say that is that just because of the lattice mismatch from the substrate. But then then if it is right, then when you change the substrate, then you may have a different like a critical thickness to see the kind of feedback.
Right. Yeah. So I don't know whether there's other like alternatives of substrate to make this grow better, but on other approach that we're taking is to explore other growth orientation. In fact, it turns out that some orientations have a lot better growth than some others, and the difference is huge because of the anisotropy of the structure. Yeah, so that's being explored at the moment. Yeah.
So it's just curious, like how much of the band gap you can actually tune by doping aluminum.
Yeah, so that's something that I always wonder, but the development here actually didn't get that far yet. So we haven't actually able to measure the exact band gap of this particular these structures yet. We are actually still in the process of getting the structure right, and then the mobility is being measured, but band gap hasn't been measured yet.
Okay.
Yeah, but we just speculate that it should be larger, but we don't have the number yet.
Yeah. It's very exciting work. Thank you.
Thank you very much. Yeah.
I also have a question about this.
Sure.
This IC and ID sites you measured.
Yeah.
So
yeah.
the model you're proposing has these gallium vacancies really close together, but our gallium vacancies themselves are charged. So how energetically favorable would that be?
You're mentioning this one right here, right?
I think on yes,
Yeah.
but I think on the next slide you have this. These two, this one.
Right. Yeah. So unfortunately, we cannot get the charge information directly, right? And one information that is missing, I mean, this can be misleading in that for that matter, which is there's no information about the oxygen directly, right? So we are showing the oxygen positions, but in this particular type of data, it is difficult to get the oxygen intensity. So all the oxygen positions are guessed. Right, so we speculated those positions. They're supposed to be there, so we draw there. But it's possible that some of the oxygen positions are empty, right, or they may be displaced, and that could certainly affect the charge of the entire area. So the short answer to your question is we don't have any charge information, and therefore I cannot say anything about how the charge is being compensated or anything like that. So that's why we wanted to calculate the energy. I mean, the run the whole thing in the DFT, but that has been pretty difficult.
Okay.
Yeah. So if you can take care of it, I'll be more than happy to work with you to get that answer.